Hi everyone. In this section today we will talk about order complexity analysis. This is a very important topic when it comes to algorithms because this is a topic that teaches you what algorithm is better than the other algorithm. Okay, so while building our code we would have certain constraints that this is the memory limit of the code, this is the time limit for to execute the code, especially when you are going to do competitive programming questions. You will find such limits with every problem. So this is the topic that comes very handy and very useful in real life as well. So how do you analyze which algorithm is better? Okay, so why do we need to compare different algorithms? Let's say we have so many sorting algorithms, so which one to use? Okay, how do we compare? Okay, so comparisons are important because you need to choose which algorithm would be a better choice for a given problem. Okay, for example, you want to buy a car and there could be different types of cars available. Okay, so in one could be a racing car. Okay, another could be a maybe a normal car. Okay, maybe you want a family car. Okay, another could be a car which is more suited for a purpose of a cab. Okay, so what do? You basically go and compare different types of cars based upon the requirements. Okay, so maybe a racing car may have a higher speed, but it may also have a higher cost. Okay, family car may be in the budget and it might be a best fit for your use case. Or maybe you want to create a taxi service, then a cab would be a better choice. Okay, similarly we have different algorithms to solve a given problem. We need to choose which algorithm is better. Like we are comparing these cars based upon their, let's say, price. What would be the price in case of an algorithm? How do we compare algorithms? Okay, so running an algorithm also comes with a cost. Okay, and this cost is in the form of a space. How much extra memory this algorithm will take? If I run this algorithm, how much space it will take inside RAM? Okay, some algorithms may not take extra space, some algorithms may take extra space, but they may speed up your time as well. Okay, so we will compare which algorithm is better in terms of space and time. Okay, so ideally our first preference is we want to reduce the time taken to execute, and second priority is to reduce the space. But for certain problems we may have constraints where space is a priority and time may not be a priority. Okay, so depending upon what kind of problems statement is given to you, you will try to find out the trade-off between space and time. Now you may ask, okay, how do we compare these algorithms? Okay, so in what sense we are going to do the comparison? Will it be a absolute time? For example, if I do a sorting, one algorithm takes 1186 milliseconds, let's say, another algorithm, let's say, takes 1024 milliseconds. Okay, so are we going to note the actual time? So if we note the actual time, it is known as experimental analysis. I will also show you one example, but experimental analysis is not worth our effort because first we need to write the code, then we need to execute it, then we need to note the time taken, and then we need to plot and see which algorithm is better. Okay, so instead of doing an experiment, we will estimate the time theoretically. Okay, we will discuss, okay, if my input size is this much, then this algorithm is expected to take this much time. So what we are going to do, we are going to do theoretical analysis. Okay, I will also show you one example how we actually do experimental analysis, but that is not needed for most of the cases. Okay, so in theory what we are going to say, we are going to say both time and space are going to be some function of input. Okay, and space is also going to be a function of input. Okay, so it may happen that your time may grow linearly. It may happen that this function could be a quadratic function. Okay, it could be a quadratic function, it could be a linear function, it could be a constant function. Okay, so you can have so many different types of functions that can fit here. Okay, if you have a quadratic function, we will say that time is proportional to n square. So if your number n changes from n to 10n, let's say, then your time for let's say sorting n integers is n, is t. Then if you go from n to 10n, your time will go from uh, like 10 square into t. Okay, so this is what is the meaning of a quadratic complexity. Okay, so if my input is, let's say, n, and it takes 1 second to execute, then if I change my input to 10 times of my actual input, okay, then my time goes from 1 second to how much? 100 seconds. Okay, that means this quadratic time is going to grow very fast. So generally what you will see is, you will see different types of plots, time versus n. Okay, so a linear plot would look something like this. That means time is a function of n. A quadratic plot would look something like this, that it is a function of n square. Okay, and we generally depict these complexities using a notation which is known as big O notation. Okay, so what we are going to do, we will talk about big O notation, order of n square. So this basically tells us our time is some function of n square. Okay, so I can say time t of n, let's say this time is some cn square. Okay, we can have some constants plus minus, but we are not worried about that. We are worried about the biggest term. Okay, that is n square. Okay, that is in terms of n. So we generally ignore these constants. It could be 2n square, it could be 5n square, it could be 10n square. We are not worried about constants. We will write something like this, that your time follows a quadratic complexity. It is order of n square, or time is order of n, or it is log of n. Okay, or it is constant. That means irrespective of your input, your time does not change. It is going to take constant time. For example, if I say find largest element in a sorted array. Okay, in a sorted array, so in this case you don't know, you can say how, it doesn't matter how big the array is, we know the last element would always be the largest. Okay, so we can find out the largest element in constant time without iterating over the array. It will not depend upon how big the array is. So we can say it can be done in constant time, and constant complexity is written as order 1 complexity. That means your time does not change according to the input. So we can say this is nothing but O1. Okay, we may also have something very high. This is known as exponential complexity. This is 2 raised to the power n. Okay, in sub problems we will also see they follow a exponential complexity. Okay, so we are going to note time and space as a function of the input size, and this would be the focus of this section. We will try to cover certain examples as well, and in the next lecture I will tell you how you can actually measure the runtime of the algorithm, and we will do an experiment and analysis. Okay, hi everyone, in this lecture we will learn about experiment and analysis, and I will teach you how you can actually measure the time of a execution of a program. Okay, so what we are going to do, we are going to learn how to actually measure the runtime. So I have a small program. So first of all, what we need to do, so every programming language comes with a library in which you can get the timestamp. Okay, let's say in C++, this library we have is ctime. Okay, and what we can do is, using this library we can note what is the start time. Okay, so it will return us some timestamp. Okay, and let's say what is the time currently when this statement, when this line number 20 is executed. Maybe this time is something like 11864889, something like this. Okay, so this is a timestamp. Okay, and it actually denotes, we can convert this timestamp into current date and time. It is with reference to certain date, maybe something of 1982 or something like that, but we can definitely convert this into today's date, whatever it is. Let's say 8th of July, and the time is like 6 p.m. 40 minutes and 384 milliseconds, something like that we can do. But what we can do is, we can actually call the clock method, and it will give us the current timestamp of the system. Okay, and then after that, what I'm going to do, I'm going to note how much time this sort function is going to take. So I've created an array. I'm not noting down the time of creating an array. I'm going to just note down the time of sorting an array. Okay, so I call the sort function on this particular array. Okay, and this will tell me, okay, this array is going to take this much time. So we do the sorting of the array, and finally we are going to note what is the end time. Okay, when the sorting is finished, then line number 22 to execute, we will note down the end time. That is also the current time of the system. And finally, if you do end time minus start time, you will get to know, okay, this is the time that is taken by the algorithm to run for a given input. So I'm going to accept the number of elements from the user, and for different inputs we are going to check whether the time remains same, does it changes, and if it changes, by what factor it changes. Okay, so let's run this code dot slash time compare. Okay, I need to build it first. Okay, let's build the code first. Yes, it has been built, and now we can run the code. Maybe I say, okay, I just want to run it for 10 elements, then the answer is 11 milliseconds. Okay, and every time you're going to run, it is going to vary slightly, because it's not that accurate. During when a process is executing, the CPU also switches to some other tasks as well. Okay, but now you can see it is somewhere around 6. So maybe I can write that time taken by this merge sort for 100 element is, let's say, 10 milliseconds or microseconds, whatever is the unit. I'm not sure, but now let us run it for 100 elements. Okay, so it almost remains same. It is almost like constant. So maybe this was 6 and this was 10. Okay, and maybe I also try to run it for, let's say, 1000 elements. Then it is going to be sorry, so let me do one thing. We started from 100 elements. Okay, so we don't have the table for n equal to 10, so let's start from 100 because 10 is a very small number to sort. So this took 10 time and this 1000 took 13 time. Okay, and now let us do it for 10,000 elements. Okay, and it took 47. Okay, let us do it for 1 lakh elements. It took 414 time, and let us do it for a million elements, and it took 2179 time. Okay, so you can see the time is growing as we are changing the input size. Now the same thing we can run on bubble sort, which is a different type of a sorting algorithm. So what I'm going to do, I have this code for the bubble sort ready, and I will not print the array. So I will what I will do, I will do the same thing here. I will include the library hash include c time, and I don't need this comparison here, and I have to create an array. So maybe I can simply copy this thing here, or I can actually copy the algorithm from this file in this file. Okay, and instead of calling the merge sort, we can actually call the bubble sort method. So here we are using vector instead of an array, which is fine. And okay, so we have this vector which is passed by reference. All right. So instead of calling the sort function, we are just going to change the algorithm. So we are going to change bubble sort array and n. Now we are going to this is a okay, compare method was used here, so we can actually copy this method and paste this method here as well. Fine, so bubble sort code is ready, and now we can note down how much time this bubble sort is going to take. So let's build the code and let us try to run this file again. So first we are going to run it for 100 elements, and it took 142 milliseconds. Okay, so now you can definitely see there is a huge difference between merge sort and this bubble sort. Then let's run it for 1000 elements, and it took 6325 milliseconds. Okay, and then we are going to run it for, let's say, 10,000 elements. It took 508902. Okay, 508092. Okay, a lot of time. Let's increase our input size by a factor of 10, and now you can see for 1 lakh elements it is still running, and it's going to take a lot of time. Okay, so let us wait this Alright, so it took a lot of time. I paused the video so that you don't have to wait to see the result. So now you can see that what actually happened is we changed our input from, let's say this was n to 10n, and you can see the time actually almost grew by a factor of 100. So this went from n to 10n, and time went from t to 100 times of t. That means uh, so that means the bubble sort is actually following a quadratic complexity. Okay, so this time is how much? 4949 uh 506410. Okay, 506410. So that is a huge time. We have to wait for a lot of time to see this result. Now if I run it for 1 million elements, this gave me very quick result, but for this the order would be something 100 times of the previous result, because again we are increasing our input size by a factor of 10. So that means it would be huge time. It would be few minutes we have to wait to get the sorted array. So that's something you should not be doing for every problem. So you should be able to estimate how this factor came or how this factor came. That is what we are going to learn. So this growth factor is actually a n log n factor. We will learn why it is n log n and how it is n log n. But here you can observe this time is proportional to n square. Okay, that means if input changes by a factor of 10, the time will change by a factor of 100. So this is what experimental analysis is, and this is what we will learn in this particular section. Okay, so that's all for this lecture. Thank you. Hi everyone, in this lecture we will learn about theoretical analysis of space-time complexity analysis. Okay, so what we are going to do, we are going to learn about a notation which is known as a big O notation. So what this notation does, it basically provides us a mathematical notation to understand the complexity of an algorithm, or to represent the complexity of an algorithm. So let us say we have an algorithm whose maybe time is some function of n. Maybe let's say the time is like a n square plus let's say bn plus some constant c. Let's say it follows a quadratic curve of this particular form. So how do we represent this function in the form of a big O notation? So it's very easy. In order to convert any function into big O notation, so what we do, we write a O followed by, we ignore all the uh, you can say constants a, b, c, x, y, z. We only are concerned about the value of n, because time is dependent upon, like time is going to shoot as the value of n is going to change. And also in n you can see there are two terms, one is n square and another is n. So we will take the term which has the highest power. So the highest power is n square. So we can say this is nothing but its order of n square. So this is how we are going to use this big O notation. And what it basically tells us, that in the worst case, whatever is the time complexity of this particular algorithm, let's say this is this curve a n square plus b n plus c. So it basically tells us in the worst case our time is not going to exceed the value of order of n square. So this can be written as, let's say, kn square, and whatever is the function, it can be written as, it is going to have value less than equal to some kn square. Okay, for some value of k. Basically it tells us in any case the complexity of the algorithm is not going to be n cube, it's not going to be n4, everything would be below n square. Okay, so what we will do is we will look at certain common complexities that we will encounter. So we will discuss examples of order 1 complexity. This is how order of log n. So you can see log n is actually a very good complexity. It grows very slowly over the time. Linear is this order n log n is slightly higher, and order n square is pretty bad. N cube is more bad, and 2 raised to the power n is very bad. Okay, so we have exponential complexity for some examples, like when you want to find subsets, they will end up getting an exponential complexity. okay, and maybe you're finding the largest number in a sorted array, so that will have the least complexity, that is order 1. This is exponential. In between you will find order of n log n for some problems, sorry, order of, let's say, n square, order of n square, which is better than 2 raised to the power n. We have order of n log n, which is better than n square. We have order of n, and we have order of log n, and we have order of 1. Okay, so in this order, so if you have a problem which can be solved in n cube, and maybe using some approach you can bring down the complexity to n square, maybe using some approach maybe you can bring it down to the order of n log n. When we talk about optimizations, the idea is to reduce the time complexity of the algorithm by using the appropriate data structure, or maybe by using a technique like sorting or searching. So when we are learning about data structure, we will also learn how to apply these data structures to bring down the complexity of problems. Okay, so now what we will do going forward is we will do theoretical analysis, and I will show you some examples how to analyze loop based code, how to analyze sorting algorithms such as bubble sort, how to analyze searching algorithms such as binary search, factorial, merge sort, polynomial evaluation, Fibonacci, and we are going to do all these examples one by one. So let's start from the next lecture. Hi everyone. So now we are going to understand theoretical analysis with the help of one example. So let's say we have a code which follows the following kind of a pattern. Okay, we have two nested for loops. The first loop goes from I equal to 0 till I less than equal to n minus 1, and I is incremented. Okay, and inside it we have another loop which starts from I plus 1, goes till n minus 1, and j also gets incremented linearly one by one. So we want to compute the time as a function of n. So let us try to figure it out. Okay, so we need to count how many times these two loops are going to run together. So inside these two loops we are doing a constant work, so this work can be written as k, but these loops are going to run some number of times. So let us see what happens when the value of I is 0. How many times the inner loop is going to run? It is going to run from 1 to n minus 1, that is, it is going to run n times. Okay, and when the value of I is going to increment to 1, the inner loop is going to run n minus 1 times. When I is 2, it is going to run n minus 2 times, and when I is equal to n minus 1, this loop is going to run just one time, or it is going to just run 0 times. Okay, so effectively if you look at this pattern, how many times these two loops are going to run? So it is nothing but it's the total work that we are doing. It is constant into the number of times these two loops are going to run. So it is n plus n minus 1 plus n minus 2 plus up to 1. So you can see this is nothing but k times summation of n, and summation of n is nothing but n into n minus 1, n into n plus 1 by 2. So this function looks something like this. It becomes kn square by 2 plus kn by 2. Now we see that this is how the time is dependent upon this particular function, and in terms of big O notation we can say this is going to be order of. So both the loops together are going to run approximately n square times, hence the complexity of this code is order n square. That's it. Let's see one more example in the next lecture. Hi everyone. So let us look at another loop based code and try to find out the complexity of this code. Okay, so this is going to be a bit tricky. If you look carefully in this example, we have two variables, one is n and one is k, and let's say k is a constant which is less than n. Okay, this is something we can assume for now. So the outer loop you can see is going from I equal to 0, I less than equal to n minus 1, and then we have this update I equal to I plus j, and the inner loop starts from I plus 1, it goes till k, and then the j is incremented. Okay, now if we want to see how many times the outer loop is running, we cannot figure it out because j is also a variable, But if you look carefully, what is going to happen when this inner loop is going to get finished, okay, the value of j would be exactly equal to k. Okay, so after this loop, j is going to be equal to k, and this can be replaced with the value of k. That means always whenever I is incremented, I will take a jump of k. For example, let's say n is 30, and let's say the value of k is 3. Then if you talk about the outer loop, I goes from 0 till 30. How many times this is going to run? So every time it is happening, I equal to I plus k, it becomes, let's say, 3, then it becomes 6, then it becomes 9, and so on. If I talk about how many times this outer loop is going to run, it is going to run effectively n by k times. And inner loop, let us assume even if it starts from, let's say, 0, okay, inner loop, in the worst case, we can say it is going to run k times. Okay, it is going to run k times. Now if you look carefully, this can be updated. Okay, so let's assume this goes from 0. In the worst case, it is going to run k times. So if the outer loop runs n by k times, the inner loop runs k times, so effectively both of them together are going to run order of, okay, so although this looks like a nested loop, but it is not. So what is happening is, outer loop is going from here to here, the inner loop is traversing this part. The outer loop is going from here to here, the inner loop is traversing this part. Okay, so effectively both the loops together combined are going to cover this entire range of n in linear time. Okay, so the overall complexity of this code is going to be order of. So I hope you understood this example as well, and that's all for this lecture. Hi everyone, so now we will look at one more example. We will try to analyze the complexity of bubble sort algorithm, and we will talk about two different cases. One is the worst case and one is the best case. Okay, so the best case would be the case in which your algorithm is going to run for minimum number of iterations. Okay, so minimum iterations, we need to figure out when the algorithm will have minimum iterations. That would be the best case. Okay, and worst case would be the case in which the algorithm would have maximum number of iterations. Okay, so what we are given, we are going to, given this code, given this logic that we know how to implement bubble sort, and what we can do is we can count the number of times these two loops are going to work together. Okay, so the bubble sort that we have, it's a slightly modified version of the bubble sort. Okay, and in this algorithm what we are doing, we are taking a boolean variable swapped, and in the first iteration what is going to happen, let's say the array is 1 2 3 4 5, then we say swapped is false, and we go from 0 till this particular element, and we check whether 1 is greater than 2, 2 is greater than 3, 3 is greater than 4, 4 is greater than 5. The answer is none of these conditions is true. So this if block will not execute, and what will happen, we will come out of this loop and we will check if swapped is true, break. So we are basically going to break the outer loop. Okay, so what we did, this array was a sorted array. Okay, this array was a sorted array, and our loop will break. So that means in the best case, if your array is a sorted array, only the inner loop is going to run for all values of j starting from 0 till n minus 1, and the outer loop is just going to run only once. So this is the best case. So we can say the best case complexity of this bubble sort is going to be order of n. Now let us talk about the worst case. The array is a reverse sorted array. Okay, so that would be the worst case, and that would involve the maximum number of swaps as well. Okay, let's say 5 4 3 2 1. We are going to talk about worst case. So again we need to count how many times these two loops will run together when we will have the worst case. So when I is 0, so we know j is going to run n minus 1 times. When I is 1, it is going to run n minus 2 times, and when I is equal to n minus 2, it is still going to run 1 or 2 times. Okay, So you can see it is going to form this series. So if I talk about the total work that we are going to do, this work is constant, this work is also constant. So effectively these two loops are going to work for order of n squared time, because this we have already seen that this sums up to summation of n and multiplied by some constant work, and this turns out to be this complexity, okay, because this is equal to n into n plus 1 by 2. So I hope this is clear. So that this we also saw in the example that we draw here, that the bubble sort grows quadratically if input size changes. So that's all for this lecture. I hope you understood the complexity of bubble sort. Hi, so now we will talk about another example, that is a binary search code, and you have already learned about binary search algorithm as well. So what we are going to do, we are going to figure out what would be the complexity of binary search algorithm. So let us first try to do it intuitively, and then we will also see it in the code, okay? So intuitively, what if you want to see what binary search does, it takes in an array of, let's say, size n, and in each iteration it finds out the midpoint, that is a constant work, and accordingly it moves the start and the end pointers, okay? So let's say start is here, end is here, and after the next iteration this part of the array is discarded. So we do some constant work and we reduce our array to size of n by 2, okay? So we get a size array of size from n, we get an array of size n by 2. From n by 2 we again get an array of size n by 4, okay? Then in the next iteration it would be n by 8, and in the next iteration it would be n by 16. And doing this after some k iterations, we know this array will contain exactly one element, okay? So after, let's say this is after in the 0th iteration, this is in the first iteration, this is in the second iteration, this is in the third iteration, and let's say in the kth iteration it is equal to n by 2 raised to the power k, okay? And we also know that this is going to be equal to 1. So I want to find out how many times the loop is going to work. So effectively loop is going to run k times, okay? So in k steps I make something from n till 1 by dividing it by a factor of 2. So I can say n divided by 2 raised to the power k, this thing should be equal to 1, okay? Because in the end we are only left with one element, okay? So I can say n is equal to 2 raised to the power k. That means k is equal to, if I take log on both sides, log of n to the base 2, okay? That means the loop in binary search code is going to run log of n times, and that means our total work done is also order of log of n. So the binary search is very fast because this log n complexity grows very slowly, and you can see if you have, let's say, n equal to roughly 1000, okay, and if you do linear search, then linear search is going to take how many iterations? Linear search is going to take 1000 iterations in the worst case, okay? But binary search is just going to take 10 iterations, okay? Or log of 1000 to the base 2. So this is going to be roughly approximately 10, okay? So if n is, let's say, 10 power 6, so what is this value going to be? So it is going to take 10 power 6 iterations. Let's say you do linear search, but binary search is just going to take how many? So I can say it is nothing but log of 1000 and square of this term, it is 2 log 1000. So it is roughly going to take 20 iterations. Similarly, if you have 10 per 9, then it is going to take 10 per 9 iterations, but binary search is going to take log of 10 power this is 10 power 3 raised to the power 3, so this is just 30 iterations, okay? In 30 iterations you can reduce a array of size 10 power 9 to array of size 1. That means it's going to be very fast, okay? And another thing I can tell you is when you talk about online judge, okay, so in an online judge you roughly have a time limit of 1 second, okay? 1 second means your program can run up to 10 per 8 iterations, okay, or this much instructions can be executed roughly, okay, so depending upon the processor. So mostly for most online judges, the processing power is this much available. So if you have a code in which you're doing a work of 10 power 9, okay, so and you're doing something in linear time, so how much time you're going to take? So 10 power 8 takes 1 second. That means 10 power 9 is going to take 10 seconds. And if your time limit is 1 second, then this 10-second code will not work and you will get a time limit exceeded error. But if you use binary search on a search space which is this big, 10 power 9, it can reduce the number of instructions to just 30, and these 30 instructions can be executed very fast, okay. So in 1 second, 10 power 8 instructions take 1 second. That means one instruction takes 10 power minus 8 seconds, and 30 instructions will take 3 into 10 power minus 7 seconds. That means this is the time that you will take to execute a code in which you are using the logarithmic complexity on an order of 10 power 9, okay. So this is how we will actually use this analysis, okay. So I hope you are getting this. And now this is the code of binary search, and what we have done, we have computed how many times this loop is going to run. So I hope you more or less understood this. There is one more method to compute the time complexity, and that is by making equations, okay. Let us see. So let me say that T of n is the code, is the time to do a binary search, okay. So what I do to do binary search, I find out the midpoint, I do some comparisons, that everything that takes a constant time of k. Then I said I reduce my problem from problem of size n to a problem of size n by 2. So I can say in order to do binary search in this problem, the time taken is T of n by 2, okay. That's it. Now I can say T of n by 2 is nothing but again some constant work plus T of n by 4, okay. Then I can say T of n by 4 is nothing but again a constant work plus T of n by 8. So I can keep on doing this till I get T of 1, which is again constant work plus 0. Then if I add all these equations, then you can see these values will get subtracted or removed, and T of n is left as summation of k. And how many such equations I am going to have? So I'm going from n to 1 every time by dividing by a factor of 2. So I'm going to have log of n equations, okay. So it becomes k into log n, and you can see this is nothing but order of log of n. So that's it. That's how we can also derive the complexity mathematically. So I hope this is clear, and I will see you in the next lecture. Hi everyone. So now we are going to analyze the complexity of merge sort. So merge sort, as you know, it's a divide and conquer based sorting algorithm, and it has 3 main steps that we already know. So let us see what it does, okay. So it's a recursive algorithm, and for many recursive algorithms we will see the equation method that we have discussed comes very handy, okay. So we'll form an equation for the time complexity of merge sort, and we will try to solve it. So what it does, so in this method merge sort, we said we have an array, we break it into 2 parts, okay. We sort the 2 parts and then we try to merge them. This is what we actually do. The first is breaking into 2 parts, okay. So this is a base case, this take constant time. So every time we check base case, we spend a constant time. Then we have finding out the midpoint, this also takes constant time. Then we have merge sort on this part, okay. So let's say the time taken to merge sort on the entire array is Tn. Then for the smaller part it is going to be T of n by 2, okay. So we can say this is T of n by 2. This entire array takes T of n. This is also T of n by 2. And then we have a merge function which we know combines the 2 arrays in linear time, okay. So it takes linear time to combine the 2 arrays. So this time would be linear, so that means it can be written as k into n. So we can write T of n as k plus T of n by 2 plus T of n by 2 plus kn. So if I try to simplify this, it becomes k plus 1 into n plus 2tn by 2, and we can still write it as some constant c into n plus 2tn by 2. Okay, so I can put k plus 1 as c, it's a constant. So this is the recurrence that we need to solve to find out the complexity of mod sort. So let us try to solve this recurrence. So we have t of n as k of n plus 2t n by 2, and t of n by 2 can be written as k of n by 2 plus 2t n by 4. T of, but now what I have a 2t here, I have a t here. I want to cancel out these terms, so I will multiply this entire equation with 2. Okay, so let's say this would become something like this: 2, this would become 2, and this would become 2 into 2, that is 4. Okay, 2 into 2, that is 4. Now what I have next is I have t of n by 4 as k of n by 4 plus 2t of n by 8. Okay, now again what I need to do is I have a 4t here, I have a t here. I need to multiply this equation with 4, so it becomes 4kn by 4, and this will now become 8. So similar thing will go on for all of these equations. We will have something like t of 1 left, that is again k of n by 2 raised to the power something something x. Okay, and plus 0. So what we will do is this would effectively become very small. Okay, so all of these terms would get cancelled, and okay, so what we are left with is we are left with terms like these: k of n, k of n, k of n. So effectively you will also multiply it with some 2 raised to the power x, 2 raised to the power x, and this will go off. So what you will observe is from every equation you are left with kn, this 2 goes off, you're left with kn, this 4 goes off, you're left with kn. So from the left we are left with t of n, and from the right we are left with k of n, and summation I goes from 1 till how many equations you are going to have. Okay, so you're going from n to 1 every time, doing every time dividing it with the factor of 2. Okay, for example, if n is 16, it becomes 8, then it becomes 4, then it becomes 2, then it becomes 1. So how many iterations did it took? It took log of 16 to the base 2, that is 4. So effectively we have log n such equations. So if you do this, it becomes k of n into log of n to the base 2, and talking about the complexity, it becomes order of n log n. Okay, so this is why we said the complexity of mod sort is n log n. So I hope now you understood why and how the complexity of mod sort algorithm is n log n, and it is much faster than what we have seen for bubble sort. Okay, so this is a n log n complexity. So roughly it's linear because log n factor is very small. So roughly it is growing linearly with the time. Okay, so you can see with every increment in a factor of digit, we have one more digit added in the time. So roughly it's close to linear. Okay, so that's it. That's all for this lecture. Hi everyone, in this lecture we will talk about how you can figure out what complexity will work for a given problem. Okay, so in an online competition you're generally given constraints. Okay, for example, you're given the number of test cases, you're given the value of n, you're given the size of the array, something like that. Okay, generally you have the constraints in any online problems, and you also have a concept of time limit. Okay, so for most problems it is 1 second, but for different programming languages it may be 2 seconds to 4 seconds. So let us assume the time limit is between 1 to 4 seconds, and in this time limit, depending upon like for Python it could be 4 seconds, the same could be done in C++ in 1 second as well. So generally the number of operations that your online judge CPU can execute Okay, it is like 100 million operations, okay, in this time frame. That means they are 1 million is 10 power 6, so then it means it is 10 power 8 operations that can be done. Now suppose if you're given an array which is of the size 10 power 4, okay, and you want to do some work, let's say assuming there is only one test case, okay, there is one test case and you have an array of size n power 4 and you want to build an order of n square algorithm on this array. It will take 10 power 8 operations which is of this order, and hence this will pass. But suppose if n is of the order 10 power 6 and you build a n square algorithm, that means you try to do sorting using, let's say, bubble sort, it will not work. Why? Because 10 square would be how many? 10 power 12 operations. If 10 power 8 operations take 1 second, then 10 power 12 operations will easily take 10 power 12 by 10 power 8, that is 10 power 4 seconds. So you're bound to get a time limit exceeded error. Okay, this is a trick that you can use to identify whether the solution that you are thinking will pass or not. Okay, then what complexity would pass this value, you need to think. Okay, so if you have 1 million, so generally the complexity that will pass is it should be of the order of n log n or lesser. Okay, so n log n means n is 10 power 6. Okay, log of n is roughly 6, assuming base 10, although it is base 2, so it would be of the order 10 power 7. Okay, that means which is less than 10 power 8 operations, and hence this code will take almost 0.1 seconds to run of this order. Okay, it could be 0.13, 0.18 or 0.20 of this order, which is still less than 1 second, and hence this complexity will easily pass on your online judge. Okay, so the constraints are given so that you are able to think of the complexity of the algorithm that you are thinking will pass or not. Okay, that's the whole idea of giving the constraints. So I hope you understood how you can identify a complexity of a problem given on an online judge, and that's all for this video. Hi everyone, in this video we are going to talk about some common complexities that will pass the worst case given this constraint. Okay, so if n is very small, let's say up to 11, then you can use an algorithm that has up to n factorial complexity or up to order of n raised to the power 6 complexity. For example, if you want to find permutation of a string which has a length 10, you can easily do it because permutation takes n factorial complexity, and this will pass the 1 second time limit. Okay, so I referred this table from CP3 book, which is a popular book by Stephen Halim on competitive programming, and he has given some examples. For example, if n is of the order 10 power 18, you can use it, you can solve a problem up to this complexity, n square into 2 raised to the power n. Okay, and so these constraints are written so that the total number of operations still remain of this order 10 power 8 operations, that is 1 million operations. So if you increase the complexity by a factor of n or log n, it is going to exceed this number of operations and you're going to get a time limit exceeded error. Okay, similarly, if n is 100, you can use an algorithm that is n4 algorithm. Okay, if n is 400, you can use a order of n cube algorithm. An example of this algorithm is Floyd-Warshall algorithm. Okay, that we have done in this course. An example of this is second case, DP with traveling salesman, like DP in TSP. So we have done this problem in the course. If n is of the order 2k, then n square log 2n, this will pass. For example, you have some nested loops, 2 nested loops, plus you are doing some binary search maybe. Okay, this will take this complexity. Then order of n square, it's simply bubble sort, selection sort, or again 2 nested loops. Okay, or maybe some basic sorting algorithm like bubble sort. This would have this kind of a complexity, n log n. So if you have, generally a lot of problems have n up to 10 power 6, in that case you need an algorithm which is at least n log n or even better. Okay, so n log n or better, for example merge sort, quick sort. Okay, and we also have 100 million, that is 10 power 8 operations. So in a lot of problems you may find 10 power 8 operations. So worst case could be order of n, because that is equal to this one, or it could be log n, or it could be a constant operation as well. So you cannot exceed more than n. Okay, so in many problems, linear search or any other problem, in many problems you will have this kind of a complexity as well. So you do not need to memorize this table, but this is to give you a general idea that you can actually remember, you can have a high level idea. Okay, if n is of the order 100, and if I do a n4 algorithm, it will take n 10 power 8 operations. Okay, and that means you should not exceed the complexity by n4 for n equal to 100. But if n is 1 million, you cannot use n power 4 algorithm. Okay, so that's the thing that you have to keep in mind, and that's all for this video.